All right, we've been doing this ever since we got into derivatives. The roots and radicals are just fractional exponents, which means we're going to use the power rule on them. And that's not going to change with roots and radicals in integrals either. So let's take a crack. Now, naturally, since it's power rule we're looking for, your u is almost always going to be whatever's under the square root. So in this one right away, I'm pretty much going to guess that this is my u. But just to be sure, let's rewrite this thing a little bit because, hey, it's kind of weird that if this is our du, it's kind of in the wrong place and stuff. And we also want to rewrite the root as a fractional exponent so we don't make any computational mistakes. So rewrite this as x squared plus 2x minus 1 all to the 1/2 power times x plus 1 dx. Alright, so now it looks a lot more like a power rule. Let's see what would happen if our u is x squared plus 2x minus 1 like we think it is. Then that means our du is going to be 2x plus 2 times dx. But check it out, that's not quite what we have. We have x plus 1. Now normally if something didn't match up this bad, we would walk away, but look at how close it is. I mean, they went to the trouble of giving us x plus 1 in parentheses, which is a little suspicious that, wow, that must be really close to matching the du. It's just kind of a hint that if they give you something that complicated as part of your du, it's probably going to match up. And sure enough, if you look at it real close, if we just multiply this by 2, if we multiply x plus 1 times 2, we'll get what we need. So if we just multiply this stuff by 2, and then divide by 2 at the same time, we do our standard thing of sticking in some constants, right? So at this point, our du and our u do match, because we have 2x plus 2 dx. So we can just integrate this. Why not use the u sub method? So 1/2. Rewrite the original problem in terms of u instead of all this junk. And if you're not familiar with what I'm talking about, go back and watch the second video in this chapter about how to show your work, because a lot of teachers make you do it this way. They want you to rewrite this as just u to the 1/2. And then of course all this du stuff is du, so that you can just integrate like a simple power without having to worry about all those x's and stuff. So 1/2 u to the 3/2 over 3/2 plus c. Of course we've got a lot of exponents we can combine here. Dividing by 3/2 is really the same thing as multiplying by 2/3. And the 2's will cancel, so we end up with 1/3 u to the 3/2 plus c. But we're not done yet. We got to switch back in, sub back in for u. So we'll get 1/3 times u, which is x squared plus 2x minus 1, all to the 3/2 power, plus c. All right, pretty sweet. Good times. These will only get worse. All right, roots, yep, they're fractions like we said. So obviously this one you'll definitely want to rewrite in fraction form, in a fraction exponent form, because it's going to be a negative and stuff. So that p squared, now before we even rewrite anything, you can sort of look at this and see, yeah, it's probably a power rule, because if your u is going to be whatever's under the root, 2p cubed minus 1, your du is going to be something p squared, and of course we have a p squared. So we can rewrite this with pretty good confidence that it's going to work out for power rule. So 2p cubed minus 1, that's the negative 1/2 power because it's in the denominator as a root. And then the p squared we think is going to be part of our du. So in this case, if u equals 2p cubed minus 1, since that's what the power's of, then our du is going to equal 6p squared dp. It's really hard to write p's when you've been writing x's for so long. Alright, so do I have 6p squared? Not quite. I need a 6, which of course requires me, to put a 1/6 out front to compensate. So now it is set up nicely, so we got 1/6 times the integral of u, the negative 1/2, du. Great, so that's 1/6. Now if we add one to the exponent, the new exponent is positive 1/2. And of course we have to divide by that new exponent as well. But dividing by 1/2 is really just like multiplying by 2. Alright, plus c, so that leaves us with 2/6 is 1/3. And then we got 2, you know what, might as well write it as a root, because hey, it's just a standard square root, because anything to 1/2 is just a square root. And of course we put our u back in, plus c. Or you could have left that as a 1/2 power. Most teachers, don't seem to care whether you sub back in for roots or just leave fractions as exponents. All right, multiplying works. What do I mean by that? Well, right when you walk up to this thing, you should have a little bit of nervousness because you're like, it's a power rule. You know, it's probably a power rule. I don't know. The only thing I see here that could be anything I've ever seen before is the square root of x. So you might be thinking, hey, my u could be square root of x. That's the only obvious candidate here, is something to have a power to it. But the problem is, oops, not a square root of x, just x. Because it would be x to the 1/2 is the power you'd be integrating. But the problem is, if your u is x, your du is just dx. But we've got all this junk, x plus 1. What are you going to do with that? There's not much you can do with it. But it turns out we could just not FOIL this, but like distribute it, you know, because we have 2 terms times 1 term. So we could just make this integral from 0 to 1 of x root x plus root x. And now it's basically just a polynomial. So we can take a swing at it. I'm going to switch these to fractional powers to make it easier to understand, because x times root x I can't integrate, but x to the 3/2, which is what that is, no problem. If you're wondering where I got the x to the 3/2, it's just x times x to the 1/2. Of course, x is just like x to the 1, so when you multiply 2 powers of x, you add the exponents. So 1 plus 1/2 would be 3/2 plus x to the 1/2 dx. And now we don't even have to match du's or anything. This is just integrating a polynomial. So that is going to be x to the 5/2 over 5/2 plus x to the 3/2 over 3/2. And we don't need the plus c because we're evaluating from 0 to 1. So dividing by 5/2 is the same as multiplying by 2/5. And dividing by 3/2 is the same thing as multiplying by 2/3. And again, we're evaluating from 0 to 1. All right, this is where we just plug in our numbers. So if we plug in 1, we get 2/5 plus 2/3. And then I have to subtract and then plug in the bottom limit, which is 0, but of course that's just 0. So I get 2/5 is my answer. 2/5 plus 2/3. Better if that was a common denominator, so this will become how many 15ths? Got to multiply by 3 over 3, so that's 6/15 plus 10/15 equals 16/15. All right, a little bit tedious, but as you can see, when you have something that's where the powers aren't very high, you can just distribute it and everything might work out pretty well. All right, so that was what happened when you have 2 things multiplied. This is kind of the same exact situation, except they're divided. And this is something we've actually came across in an earlier integral video, where I just want to make the point that, hey, you know what? If you've got 1 thing downstairs and 2 upstairs, you can split it into 2 fractions. And that's what we should do here, because if you try to use the power rule, it's the same problem we had on the previous problem. Is this an x to the minus 1/2? Yeah, maybe, but then your du would just be dx, not x plus 1 and all that. So it turns out the way to deal with this one is just to split it into 2 fractions. X over root x and 1 over root x. So at this point, it's kind of a polynomial because that first term reduces to x to the 1/2. And that second term, of course, is just x to the negative 1/2. So we can integrate this. There's no use to worry about, it's just x to different powers. So we've got x to the 3/2. Instead of dividing by 3/2, I'll just take it straight to multiplying by 2/3. And then x to the negative 1/2, add 1 to the power, becomes x to the 1/2. And of course you divide by the new power of 1/2, which is really the same thing as multiplying by 2. Throw on a plus c, and that's all she wrote. So when you have relatively simple low power expressions like this, it doesn't hurt to split up fractions into 2. The one thing you got to be real careful of is, let's say this had been this problem, square root of x over x plus 1. I see this, students do this all the time. Even if you're in calculus, doesn't mean you remember everything from algebra 1. And this is one of those big tricks. You cannot split this into 2 fractions. So this does not equal square root of x over x plus square root of x over 1. That's just not legal. If you have 2 separate numerator terms separated by a plus or minus, yeah, you can separate it into 2 separate fractions like we just did. But if you only have 1 thing upstairs and 2 things downstairs, you cannot split that. So if you don't believe me, try just making up a couple of fractions and adding them and stuff. But it doesn't work out. All right, du in disguise. See what happens here. All right, so you can, if you look at this problem, you might think about, wow, that's really hard. You might not see what's going on here. You might think, hey, Chris, let's try foiling this out and combining terms and stuff. But it turns out there's a really subtle thing. It'll come up a lot. The derivative of root x is 1 over root x, or 1 over 2 root x. Point is that this is actually a power rule problem where 1 plus root x is our u. Because our du is just going to be and that's a 1 plus x to the 1/2. I'll just rewrite it as a fractional exponent to make it easier. So the derivative of x to the 1/2 is 1/2 x to the negative 1/2, which is the same thing as 1 over 2 root x. So now you see why this root x is actually our friend. It's part of our du. It's going to go away. So of course we want to rewrite this problem. Now that we realize our du's could possibly match up and stuff, we want to rewrite everything with exponents and stuff. So 1 plus, I'll just leave that as root x because the one I'm really concerned about is this negative 2 power. And then I got the 1 over root x, and I got the dx. Alright, so you can see that my du is actually pretty close to good. I need 1 over 2 root x. I've got 1 over just root x. So I got to put a 2 down here, which means I put a 2 out front. This 2 is downstairs, so that's why this time instead of putting a fraction out front, I put a whole number, because the fraction was actually how I got that 2 downstairs. Alright, so at this point my du matches. I got my u and all that, so I can just integrate, and we'll do the u sub method. So we'll do 2 times the integral of u to the negative 2 du. The problem is I got to switch my limits of integration here. So we'll take our original limits and plug them into our u equation. Plugging in 9 to this equation gives me 1 plus 3 is 4. And then taking the original 1, plugging it through here is 1 plus 1 is 2. Alright, so this is going to be 2 times, and what's the integral of u to the negative 2? It's u to the negative 1 over negative 1, so that's just negative 2 over u, evaluated from 2 to 4. Alright, so what's that going to do for us? So that's going to be negative 2 over our upper limit, 4, minus a negative 2 over 2. So add, so we get negative 1/2 plus 1 is just 1/2. Alright, pretty crazy, right? So the thing I just want to emphasize, the real trick to this problem was when you're initially setting it up, you just want to realize that that root x downstairs is actually part of your du. And that's one of the hardest things about the power rule, is when that du is really well hidden. Or something you wouldn't even expect would be part of a du is actually a du, etc. You just learn these by doing them pretty much, but it can get fun. Alright, so what's the deal with this one? I don't know, let's find out. So the first thing I notice is I've got a wacky power in here. So whenever you see a wacky power, a lot of times you're thinking that it might be a power rule, but on the other hand, if I made this my u, my du would be some wacky thing with thirds in it, in the exponent and stuff, but I don't have that as my du. I've got this 2x squared, so there's actually another one of those problems where you just want to multiply them together and just essentially distribute it out and get a polynomial. So if you multiply 2x squared times 3x to the 5/3, it's going to be 2 times 3 is 6, and then x to the what power? 2 plus 5/3, so that's going to be, this kind of like, 2 is really 6/3, so 6/3 plus 5/3 is 11/3. And let's see, 1 times 2x squared is just 2x squared. Ah, at least that one's not too bad. Alright, so we don't have to worry about matching du's because it's just x to some exponents. So this is going to integrate to 6 times x. We got to add 1 to 11/3. So if we add 3/3, we get 14/3. Divided by 14/3, plus 2x cubed over 3. Alright, so I needed to divide by 14/3 is really like multiplying by 3/14. So I got 3/14 times 6x to 14/3 plus 2/3 x cubed plus c. This will reduce a little bit, I think, because 14 goes to 7 and this goes to 3 if we divide each by 2. So we get 9 divided by 7, x to the 14 thirds, which if you're not a fan of fractional exponents, or if maybe if you see a problem kind of this wacky except it's got definite limits of integration, then go back on this website. In algebra and algebra 2, we've got a bunch of videos about fractional exponents and stuff. So, but basically this is the cube root of x raised to the 14th power. Pretty crazy. I would suggest taking the cube root first, then raising the 14th power, but you're free to do what you want. But that's a pretty nasty one. I mean, there are not a lot of teachers who are going to put a 14 thirds power in a problem and expect you to plug in numbers. I mean, that's just psychotic. Unless it was a 1. Because if you plug in 1 to this, I'm not saying we had to in this problem because this is not a definite integral. But if there was a 1 to plug in, 1 to 14 thirds is still just 1. And of course, 0 to the 14 thirds is still just 0. So I bet if they had a problem this gnarly, the limits would have been 0 to 1. But again, that's not this problem, so let's not worry about it. All right, so that's a power rule. We're going to see this a bunch more. Because like I said in the end of the last video, the power rule is not just going to have x's in it. You're going to see natural logs to powers. You're going to see sines and cosines and tangents to high powers. So the power rule gets used tons, because not only does it get used on strict stuff that looks like it might be a power rule, it gets used on radicals, it gets used when you have other crazy functions raised to powers. So the power rule gets used all the time. You'll get really used to making your du's match on this puppy.